My name is Professor Orata. We are continuing with our thermodynamic lecture series. So today we are going to look at steady-state flow processes. And the term steady-state is very important in the sense that this is a system where everything relatively is constant. The rate is constant, the mass flow rate is constant, and during the flow in the system, there's no accumulation of mass or energy. So it's very, very important. So it's a steady-state flow process. And now one of the first things which you have to look at is, we have been used in the first place to first law of thermodynamics. First law of thermodynamics, where we say that the change in internal energy is the same as dq minus dw. And of course, du is change in internal energy, u is internal energy, dq represents heat, and dw is work. But this is for non-flow processes. This is for non-flow process. So there's a difference now when it comes to steady-state flow processes. We're having the fluid, whatever the fluid is, it could be a gas, it could be a liquid, flowing through the system. So the first law for the steady-state flow process is not going to be the same as that for non-flow processes, like we have seen in the earlier lectures, where we had du was equals to dq minus dw. So let's just do a schematic of a steady-state flow process, and then we discuss it. So in this particular system, we have, let's say, our unit mass, which we are going to follow behavior or flow through the system, unit mass. We have our heat exchanger, and we have a turbine where the work is extracted. That's our turbine. And then we have the exit. So this is our heat exchanger. This is our turbine. Could be work done, could be shaft work. Normally involves reciprocation or rotation. Let's call it W shaft. And so we have our unit mass. Let's say there's an arbitrary datum level, which I'm indicating here, dotted line. Let's just call it a datum level. And so this is our entry. Let's call this our entry point. And this is our exit. Let's call this our exit. And let us now define some of the dimensions of this particular system. Let us say that the elevation from the datum level, the entry, is, let's call it HA, and call this section of entry, let's call it section A. And then the elevation, the exit, is, call that B, HB. And so the difference between HA and HB, we call that delta H, or DH, say is HAHB, HA minus HB. And let us also define some of the thermodynamic quantities at the entry. So we have talked of this as being unit mass. Let us say the pressure here in section A is PA, and the cross-sectional area is A, and the volume will be VA. And so at the exit, let's call the pressure as PB, the volume as VB, the area there we're talking of as AB. So remember, these are just arbitrary markings, but the system in a nutshell is we have a fluid which is flowing through the system, heat is exchanged, work is done, and then it exits. So we want to develop the thermodynamic expressions for this to see what kind of processes are taking place here. Now, the other thing which we need to now work on, let's call this section B. Let's call this portion section B. I repeat, steady state flow process things are relatively constant, the rates are constant, the mass flow rate is constant, there's no accumulation of material, and there's no accumulation of energy in the system. So let's now work with this system of ours. Let's work with the system. So one, what we want to worry about is what is the work done in the various portions. And remember, we talked of this unit mass, which is flowing through the system. Unit mass, which is flowing through the system. And don't forget that as it flows through the system, it actually does work and work is done on it. But that balances out or cancels out because it does work and work is also done on it. That unit mass which we are looking at there. So in the first section, what are we going to have? So we are saying that from first law, du was equals to dq minus dw. That is for non-flow process. Now we are dealing with this unit mass which is moving or flowing. And then number two, this unit mass is elevated from some arbitrary datum level. So it means that we must now factor in kinetic energy and potential energy. So we must factor in contributions from kinetic energy. And remember, that's the energy associated with motion, and let's call it Ke, and potential energy. Potential energy. Let's call it Pe, that is associated with elevation. So that what we are having here in the first section and the second section, we have the internal energy in section of the fluid in section 1, and we also have its internal energy in section 2. So in a nutshell, this first law of thermodynamics, this was first law of thermodynamics, now can be recast or rewritten. We can rewrite it as du, that is the internal energy, du plus dc squared over 2, and the c there represents the velocity, or we can stick with that, or we can stick with it as v, but the c there represents the velocity, and then plus g dh for the potential energy. And that must be equal to Q minus W. And remember, this W also has the shaft work. That is the work which will be extracted at the turbine. And so if we put in these quantities, which we have, the internal energy in section A and B, the change will be UB minus UA. Remember, our U here is internal energy. Very important to note that. And then C, which we are saying is our velocity, or we can call it V. We can call it C or V, which we call our velocity. It's given the second term where we have kinetic energy, which is normally half times mass times velocity squared. That is the expression for calculating kinetic energy is a half times mass times velocity squared. So if you know the body, the mass of the body and its velocity, I would compute its kinetic energy. So we will have, let us say we have here plus half the velocity in section A and B squared. And then we now have the expression for the potential energy, So we have for the internal energy, for the kinetic energy. Now we have for the potential energy will be G. Then HB minus HA. That will be given as Q minus W. And remember now, what is our W? Because we're dealing with pressure and volume. If pressure is at the entry is A, like we had said, and the volume is A, and the cross-sectional area was also A, then what we have here is now UB minus UA plus a half VB squared minus VA squared plus G of HB minus HA will be Q minus PB VB minus plus PA VA. Remember, that is work, because pressure times volume, like we have said, always remember, pressure times volume is force over area times displacement. And so the two areas cancel, so you have force times displacement, and that gives you work. So this expression represents work done in section A and work done in section B. Now, the minus sign, remember when you are looking at this VB, you have taken the cross-sectional, the volume, and you have the cross-sectional area. So if you have the volume and the cross-sectional area, remember that gives you the displacement. If you have volume, cross-sectional area, that is, these are units, so you are talking of displacement times area over area. So it's basically displacement. So you multiply that again with your area, so you will get that quantity there basically gives you pressure and volume. It's very important that you hold on to dimension analysis, because if you have the volume, remember that is displacement and area, then divided by area, that cancels that. So when you multiply that with the area, then you have your displacement times area, that is now your volume. So it's very important always to try to work with dimensions. Dimension analysis always make sure that you don't get lost, because if your dimensions don't tally to what you are determining, you cannot, for example, be intending to deal with volume, while when you harmonize your dimensions, you find it is dealing with length. Then that means something is wrong. So it's important that you use a correction factor to make sure that the dimensions are actually in agreement. The dimensions are in agreement with what you want. That's very, very important for us to always note that. Now, once we have these expressions, we clearly see that also we have the shaft work. And what is the origin of the shaft work? Remember, we had the turbine. We have the turbine. We have the fluid flowing. We have the turbine. We have the turbine. And in this turbine, you can extract work. Work can be done. Can either be reciprocating or this rotation. And like we had said, when we did the earlier lectures, we talked about the Pelton turbine, which I can just draw briefly the schematic representation of it so that you have an idea that we can do work on that particular turbine. So if you have the Pelton turbine, if you look at the earlier lectures, we have this as the nozzle, the wheel, we have our nozzle, and we have our runner. Then we have our vanes or blades. So we have this jet of steam jet or water jet, whichever it is. And of course we have the casing. This is the casing. This is the vane or blades. And of course, that is your nozzle. And that's your spear. So of course, as the fluid hits the vanes, things stand. Of course, this is connected to a mechanical unit whereby you are able to do your work. That's very, very important. And the heat exchanger, we simply are able to exchange heat. That means it's not an adiabatic system per se. In other words, you are able to exchange heat between the system and the surroundings. You are able to exchange heat between the system and the surroundings. So don't always assume anytime you're talking of heat, because in earlier lectures you have talked a lot about adiabatic heat, that you're dealing with adiabatic heat. No. In the heat exchanger, which we had drawn earlier on, remember, in the system there, that heat exchanger, there is exchange of heat. You're allowing heat to be exchanged. Now, if you harmonize this expression which you have down here, then we can bring the pressure volume quantities, that's the work there, back to the left of the equation. So you have UB plus PB VB. And then we have here minus UA minus PA VA. So we can have that as minus UA plus PA VA. And then of course plus these terms involving kinetic energy, which we can express as delta V squared plus G delta H is equals to Q minus W shaft work, assuming shaft work. And if you look at this expression carefully, you remember from our earlier lectures, we said that enthalpy H was equals to U plus PV. Enthalpy can be gotten from expressions for internal energy plus pressure and volume. And I mentioned in those earlier lectures that we take the difference, the change, then that would delta U plus delta PV. Don't assume that PV is equals to nRT unless it is specified that you are dealing with an ideal system which obeys the ideal equation of state, that is PV is equals to nRT. So don't assume that PV is nRT. If that is the case, that it is not ideal, then just put in pressure value for the system and the volume value for the system. But if it's ideal, then you can put nRT there, which will become delta N RT, and that delta N will be the difference in number of moles of gas in the reactants and the products. Now, taking cognizance of the fact that H is equals to U plus PV, we have the same expression here, U plus UB plus PB VB. So we can call this HB. And this one, UA plus PAVA, we can call that HA. So that basically this quantity here is actually DH or delta H. And if we assume that you can ignore the kinetic energy and potential energy, in other words, they are not significant. Yes, they are not significant because when you are dealing with steady state flow systems, you don't expect the flows to be very, very fast, because when you have terribly fast flows and probably the system is not coherent, then there could be a lot of turbulence, and you'll have to worry about turbulence. That we'll see later on in our series when we're dealing with fluid dynamics, especially for chemical engineering series, which we're going to do at some point. Then you worry about turbulence and so forth, and we don't want to do that. So let's assume that the flow is negligible and the potential energy is negligible. So we can say that is 0 and that is 0. So then we have DH is equals to, in the infinitesimal notation, dq. Let's go to the measurable, to measurable quantities, so that you're able to work with Q and V. Let's just say delta H, therefore, is equals to Q minus W shaft. Or in the infinitesimal notation, DH is equals to DQ minus DW shaft. So this is the expression for the first law of thermodynamics for a steady state flow process. First law of thermodynamics for steady state flow processes. Very important, very, very important. Always remember that that is the expression for first law. You notice now we are not talking about internal energy. It's captured in the enthalpy of the system. But remember that in most cases, you will have to worry about kinetic energy and potential energy. You're going to worry about kinetic energy and potential energy values in the system in certain cases. So don't always assume that kinetic energy will be 0, potential energy will be 0. So that gives us the first law of thermodynamics for steady state flow processes. Thank you. Let's stop at that point.